Swayam Prabha. Digital India. Educated India.
Welcome to Introduction to Machine Learning. Today we will look at combining different models, and that will help us increase the accuracy than what we can get with a single model. That is the primary objective, and it also gives us better robustness to certain types of errors and gives us better generalization. So let's look at how we can combine different models. So the objectives will be, we'll look at the advantages of combining different models. We will also look at different ways of combining models, and within the combination of models there are two specific algorithms that we will talk about. One is the decision tree learning and the other is adaptive boosting or AdaBoost. So the questions for today's lecture are, why should we combine models? So one of the reasons is that there are multiple models available and none of them are perfect, or none of them may have very high accuracy. So sometimes when we combine them we get better accuracy. Then you can have models that cater to different subsets of the features on which you are trying to fit the model, or different parts of the feature space. So they may have some complementary properties that may help them compensate for the errors of the other models. Now once we start combining models, there are different issues that come to mind. How many classifiers or models should we have? What kind of model should we have, and what kind of features should be used for each classifier or model, and how do we combine different classifiers? So here I'm just using classifier as an example, but we will also see that the same kind of model combination can also be done for regression. So there are different stories of success of combining models. If you look at any online competition such as the $1 million prize by Netflix to make a movie recommendation engine, or several of the competitions on Kaggle or different ML online workshops and conferences, most of the top entries are usually ensemble or combination of multiple models. So this is a trick that you should have up your sleeve to be able to get higher accuracies, better generalization, etc. So you can also see in many leaderboards for famous competitions, machine learning competitions, that the top few models are usually combination of models. So here, for example, the number 2 model itself, the entry itself, they name their entry as the ensemble. Ensemble is a specific combination of different models. So why do these ensembles work? So ensemble in a nutshell is basically averaging multiple models, and what happens is that many times different models can only look at some parts of the big elephant. So one model thinks that the distribution of the data is like the trunk of the elephant, another model thinks that it is like the leg of the elephant, another thing is like the tail of the elephant, and so forth. But when you combine all their knowledge together, the whole picture of the elephant or the entire distribution of the data, it emerges with their combined wisdom. So these are like different blind men who are touching different parts of the elephant and thinking what the elephant is like. So let's take a more concrete example. So let's say we have two-dimensional variables, right? So let me bring my pen up. So let's say we have two variables, x1 and x2, and let's say we have two different models. Okay, we have the data distribution is such that it is a multimodal Gaussian. So there is one that is sitting here, another that is sitting here, and then somewhere these contours merge, right? So it's possible that what we do is we take one model and we have that one model basically, let me change the color, maybe that will be better. So let's say we have two different Gaussians and the other one is somewhere sitting somewhere else, right? So here what we mean by this is that this could be just distribution of one class, not two different classes, and then let's say your other class actually has a distribution somewhere else. So your other class is also multimodal, okay, and we want to find a combined decision boundary between the two classes. So here it's possible that just modeling one of the modes of the conditional class distribution is not enough. We want to be able to model the multiple modes. We want to be able to model this mode as well as this mode for class 1, and then this mode and this mode for class 2. So in this case, if we have two different models and we take the average decision of the two different models, that might turn out to be better. Another example could be that we look at two different dimensions. Even if we have a unimodal distribution and we examine only the feature x1 or only the feature x2, then with respect to feature x1, we may just be modeling something like a Gaussian tunnel, which is which does not vary in one direction, and then we may be modeling another Gaussian tunnel for x2, which may not be varying in this direction. So by combining these two, by taking a product of these two, for example, we may be able to approximate the two-dimensional Gaussians. So these are different ways to think about how models get combined and they give you better results. Okay. So before we delve further into how to combine these models and some sort of proofs in simplified conditions of that these combinations work, let's first talk about the richness of models. So some models are more rich than others. What I mean by richness is that they can model a wider class of functions by varying the parameters, and some models are simpler. So to give you an example, that we can compare decision thresholds with linear classifiers, and obviously linear classifiers are richer than just decision thresholds. We will come to that in a bit, but think about it this way, that if you take the entire space of functions, so let's say we are looking at a space of functions, okay. So within this space of functions, right, the set of functions that can be modeled by one type of a model, okay, will form a set, okay. So this is called the set of hypothesis. This is the hypothesis class. What's a hypothesis? The hypothesis is that the function that I have learned is actually what is modeling the data, either the classification or the regression of the data, okay. Or it could be just density modeling, but the set of function or the function that I have chosen is good for modeling the data. So that is my hypothesis, and that hypothesis is not completely true or completely false, because it's not completely false because it comes close to the data, and it is not completely true because it does not exactly model the data. We could overfit and exactly model the data, but then it may not fit on the validation data. So be that as it may, the point is that if we look at all the set of functions that can be modeled by one type of a model, where the only thing that we may vary is the parameters of the model. So let's say we call it h of theta x, okay. So if we can only change theta, right, for different theta we will get different functions, and that entire functions in the space of all functions is this set, all right. It's possible that if we have a richer set of functions, that set may be a larger set, that may be a superset of the given set. So let's say we have g phi of theta, g phi of x, and g phi of x is bigger and h theta of x is a subset of g phi of x, okay. So that's possible. So for example, So this could be, for example, linear, and this could be polynomial. So polynomial is a superset of linear. Okay. And it's also possible that we have an entirely different set of hypotheses which may or may not overlap with these classes. Okay, so it's possible that we have something like this, okay, which is another different type of function, g h, let's say f psi of x, and that could be a completely different set of functions. So some of the functions may overlap, that can be modeled by both classes. So this is how we would like to think about hypothesis class. So when you have a classifier, if you have a linear classifier, it's one hypothesis class. If you have a neural network with 5 hidden units, then it's a different set of hypothesis classes. Okay, if you have a decision threshold in any of the variables, then it's a different set of hypothesis classes. Within the class, the hypothesis can shift by varying the parameters. So now let's look at the hypothesis class of a threshold. So if you have a single variable, right, so this is your single variable x1, your decision threshold can be anywhere. It can be here, it can be here, it can be here, it can be here, anywhere, right, and it can be such that at that threshold negative is on the left side and positive is on the right side, or it can be such that negative is on the other side and positive is on one side. Okay. So if we have a classifier that basically says, okay, ax plus b greater than 0, right, or something along those lines, right, then that particular classifier where a can be plus 1 or minus 1, we can fix it. That particular classifier is a decision threshold classifier for a single variable. Okay. All right. Now let's say if we have multiple variables, right, so let's say we have two variables, x1 and x2, but we are allowed to choose threshold for only one of the two decisions, okay, for one of the two variables. So we can either we can have x1 greater than theta 1, or we can have x2 greater than theta 2. We can also have x1 less than theta 1, and we can have x2 less than theta 2. So these are the type of functions we can have. So the hypothesis class would be any axis aligned boundary, right. So it will be either parallel to x1 axis, or it will be parallel to the x2 axis, and depending on which one we select, one side will be positive, the other side will be negative. We will not have a slanting line. Okay. For a threshold class, we will not have slanting lines. On the other hand, if we look at linear classifiers, right, so here we have W transpose X plus B, okay, whether that is greater than 0 or not, that is your hypothesis class, and that defines your class 1 or class 2. Okay. And let's say now we have x1 and x2. So here your hypothesis classes are going to be any line including axis aligned lines, okay, where one of the W1 or W2 is 0, that is also possible, but it can also have slanting lines, and then either upper side of the line is positive, or the lower side is positive, or the left side is positive, or right side is positive. All those possibilities are there depending on W and their signs, and B, which shifts the line, right. So here what we can see is that if you look at decision thresholds, that's one hypothesis class, and a bigger hypothesis class, that's a superset of this class, is linear classifiers. Okay. So the thing to note here is that linear classifier is richer. It can model a larger variety of functions than thresholds, and it also subsumes the thresholds. Okay, it's a superset of these thresholds. So what is the advantage? Advantage is clear, that we can model more complex functions, we can have lower training error, So whenever you have a richer class of hypothesis, it's in general going to have lower training error. Okay. But the question is, does it also have lower testing error or validation error? That we don't know. Sometimes by giving too much freedom to the model, to the regressor or the classifier, we may get lower training error but poor generalization, which is poor validation error. We will get high validation error. Okay, so having a richer hypothesis class is not always good, but we should be aware that sometimes we need richer hypothesis classes, sometimes we need to restrict the hypothesis classes depending on how we are doing on the validation data. So how we are doing on the generalization aspect. So restricting the classifier is regularization. It could be regularization by design. We purposefully choose a classifier that is not rich enough, okay, not too rich, let me put it that way. Or it could be because of we add some sort of a weight penalty and so forth. So there are different ways of restricting the classifier, restricting the hypothesis class. So now also let's look at linear classifiers. So this is, let's say, linear. Now on top of that we add not just this function, not just the error square, let's say not just the loss, okay, but we also add lambda by 2 times mod of w square. So let's say we also do L2 regularization on that. So depending on lambda, so if I tighten the lambda to infinity, positive infinity, I will get w equal to 0. So that's one type of a classifier or a regressor. So that is going to be a point where all the w's are 0, or perhaps not a point, maybe a small set, because b can move. B is usually not part of the regularization. So by regularizing, I am actually creating a nested set of hypothesis classes where when I increase lambda, I go towards smaller and smaller sets. Okay. Increasing lambda, increasing regularization reduces the hypothesis class. Okay. So we make the hypothesis class smaller and smaller. So that's another way of looking at hypothesis classes. So why this is important, we will see. We have till now seen how to restrict the hypothesis classes. By combining classifiers, what I will show is that you can actually expand the hypothesis class. Okay. So we already talked about nested hypothesis classes of single and multiple variables. So here let me quickly recap. So if we can only have decision thresholds on a single variable, right, x1 or x2, then I can have only this kind of a class, right. So I can only have either this kind of a class, or I can have let's say this kind of a class, right. So if I am allowed to have a decision threshold on only x1 or x2, but if I am allowed to have decision thresholds on multiple of them, so for example if I have x1 and x2 or something along those lines, then I can have hypothesis classes that look like this also. I can use, if I use and or something along those lines, if I have or, then I can have hypothesis classes like this also. So there are different ways of expanding the hypothesis class. Sometimes you increase the number of variables that are allowed, sometimes you combine multiple classifiers and so forth. Okay. So now let's look at neural networks. Neural networks form a nested hypothesis classes when we change the number of hidden neurons. So let's say if you have x1 and x2 as two inputs, and then I have a 3 hidden neurons, okay, and then they combine to give me a classification. I'm just using classification as an illustrative example, but it is also applicable to validation. Compare this to if I have only 2 hidden neurons. Okay. So the hypothesis class of 3 is a superset of hypothesis class of 2 hidden neurons. Okay. And why is that? Because I can always turn the weights coming in and out of one neuron on the neural network on the left hand side to be 0, and because of that I can actually simulate a 2 hidden neuron neural network. And if we try to look at it in x1 x2 space, right, so a 3 hidden neuron basically or approximately is a combination of 3 lines, and then you can color these lines black, you can color these half spaces that you have. Now you have 1, 2, 3, 4, 5, 6 and 7 half spaces, or 7 spaces that in general that we will have because of these 3 lines. You can color them any which way using the weights of the final layer and the weights of the initial layer. So based on that you can get different kinds of hypotheses, whereas when you have only 2 neurons, your hypothesis space would be the set of functions that can be formed using 2 hyperplanes. Okay, so one like this, another like this, something like that, and obviously the one with 3 hidden neurons is going to be a superset of the hypothesis space compared to the one that has only 2 neurons. Okay, so now let's look at what is an ensemble. For classification, the idea of an ensemble is quite simple. You have classifier 1, and you have classifier 2. Okay, and all we do is we combine their results. So how do we combine? Basically we take the, let's say if we are looking at a binary classification problem, then we just take the mode of their decision. So mode won't work with 2, we will need to have 3. So let's say classifier 3. Okay, so basically your decision is going to be, your class is going to be, so basically y is equal to mode over m. M is the number of classifiers, m is equal to 1 to 3, okay, of ym of whatever is the result that you get, right. So this is going to be for the mth classifier, whatever input you give it. Okay, so I can give the index I. Alright, so it's just the mode. So we are basically taking voting over 3 classifiers, and whichever class gets 2 or 3 votes, okay, whichever gets the majority vote, that class is declared as the class that is decided by the classifier. Now why should this work? Okay. This can only work when these classifiers are somewhat independent of each other. If all 3 classifiers are exactly the same, right, then basically if we take the mode or the voting, then it's not going to help us in any way. Okay. Or if the classifiers are adversarial to each other, whatever class 1 says class 2 is trying to sabotage it, whatever classifier 1 is saying, classifier 2 is actively trying to sabotage it by giving the opposite decision, then it is nullifying what classifier 1 is saying. So we assume that these are, we don't have either of the 2 cases, they are independent of each other. So there is an assumption of independence. Okay, that's a very strong assumption. Independence of models. Okay. It's only when the models are independent of each other that we get a strong effect of having better decisions. So now let's take an example of how these decisions can be better. Okay. So let's say we have these classes, this classifier can give you multiple different answers. So let's look at a binary classification. So the 3 different answers that we can get is 0 0 0, 0 0 1, 0 1 0, 0 1 1, and so similarly we will have total of 8 combinations, right. And so let's assume that we have class to be, the actual class is 1, okay, 0 0 1 1, 1 0 0, 1 0 1, 1 1 0, Yeah, so let's look at the 8 possible combinations for binary classification. We have 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, okay, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So let's say actual class is 1. Okay. So now we want at least 2 of them to give us a probability of 1. Okay. So which ones are going to give us a correct answer? This one is going to give us correct answer, this one, and this one. Okay. These 4 are going to give us the correct answer. Alright. So let's say for each classifier the probability of correct classification is P. Okay. So and the probabilities of the 3 classifiers are independent of each other. The 3 classifiers are independent of each other. So for any of these, for these 4 out of the 8 possibilities, the probability that we will have the correct answer is going to be, so we have 1, 2 and 3 where we have 2 of them. So P squared 1 minus P, okay, times 3 plus P cubed. Okay. So long as P is greater than half, so long as each classifier does slightly better than chance, okay, this is going to be greater than P. If P is greater than half. Okay. And we can generalize it to any number of odd classifiers and we will get the same answer. Okay. That it will, the probability will actually, in fact, it will start with whatever is P. So this is half, this is P, and it will keep increasing as we increase M, the number of classifiers. Okay. So this ensembling effect is there. Now the reason why we could multiply these, we could have P squared and P cubes and all that, is precisely because we had the independence assumption. If we did not have the independence assumption, then you cannot multiply the constituent probabilities of a joint distribution, right? So this independence assumption is there. It's a strong assumption, but it basically illustrates the point that we can combine classifiers as long as they are somewhat independent of each other. The other thing is to notice that they have to have at least some good answers. Even if P is not touching 1, it cannot be below half. Assuming balanced classes, it cannot be below half. So they have to have some learning capability, but they could be weak learners. Weak learner means that their probability of correct classification is not close to 1, but it is greater than half. Okay. So now let's look at a hypothesis class of an ensemble. If we look at simply the hypothesis class of linear classification, right? So this is your x1 and x2, and let's say we have 3 different ensembles, 3 different let's say we have 3 different linear classifiers in the ensemble. One is here, the other is here, the third is here. Okay. So now if we take the majority vote, it's possible that we can color some of these in such a way that we can actually have class 1 somewhere else, class 1 and somewhere else, and so forth. So we can now the average or the mode of the 3 classifiers, the combined classifiers, is no longer linear. Okay. It's actually a nonlinear classifier. It's similar to a neural network now, with an ensemble with 3 linear classifiers is similar to a neural network with 3 hidden nodes, okay, in some sense. So here what we are getting is we are getting an expansion of hypothesis class, expansion over the constituent. So this is a single model. Okay. Single model has this hypothesis class, its ensemble has a bigger hypothesis class. Okay. Now let's look at the same thing for regression, just for our curiosity that ensembles really lead to better results for regression also. So let's say we have three different regressors. Okay, so we have f1 of x, f2 of x, okay, and f3 of x. Okay, and let's say they are all three linear regressors. So this is w1 xi plus b, and this is w2 xi plus b. Here w1 and w2 and w3 are all vectors. So this is b1, b2, and w3 xi transpose, okay, plus b3. These are three different classifiers. All right. So now, assuming that x is let's look at the variance of the error in this case. So let's say your target was ti. Okay, so what is the expected value of ti, right, minus yi, okay, squared. All right. So what is this expected value? We would like this expected value to be low. We would like it to be lower. Okay, and what we are saying is that your yi is going to be an average of the three. Okay, it's going to be an average of three different regressors. It could be two also. Just it's an here we took an example of three. In regression, we don't have to have an odd number of constituents. We can have two regressors, four regressors also. But let's look at this. So what is this expected value? So what it turns out is that this expected value is going to be we will have this sigma 1 square plus sigma 2 square, okay, plus sigma 3 square, not divided by 3 but divided by 3 square. Okay. So what that means is that the variance of the error when I take the square root is going to be 1 by square root of 3 times the variance of the average variance of the three different constituents. So what is this sigma 1? Sigma 1 is the expected value of this first one. Let's call it f1, f1 of x minus ti the whole square. Okay, and then similarly sigma 2 is the expected value of f2 of xi minus ti the whole square, and so forth. So if the three regressors give you the same variance, right, and we are taking their average, when we are taking their average, we are going to be dividing the variance by a square root of the number of the constituents. Okay, so keep that in mind. So, but this also is only true. This is only true when we have cross terms to be 0. So the reason this comes out to be like this is that if we plug in this y here and we take difference from ti the whole squared, so what we will get is we will get a yi squared term, we will get a ti squared term, and we will get ti yi terms. So whenever we have the yi squared term, in that term we will have the square of these individual terms, and we will have cross terms. Okay. So assuming everything is 0 mean, the cross terms only go 0 when the constituents are uncorrelated. So here the f1x, so we will assume that expected value of f1x, okay, the errors are going to be uncorrelated. f1x minus ti and f2x minus ti. Okay, this is 0. This is going to be 0, only then this is possible. So they have to be uncorrelated with each other, and that uncorrelated assumption again is related to that independence assumption that we were talking about. They are not the same, but they are quite related. Only then we will get a reduction in the variance of the error, and this reduction keeps on going up as we have more and more constituents in the ensemble. Okay. Let's look at a simple model uh, of combining different classifiers. So before that, let's look at a non-parametric model of for both regression and classification, where we have no parameters, we just rely on the training data, and that is a nearest neighbor model. So let's say we have the two variables x1 and x2, and we have some training points. We don't know what the target value for them is yet, but we just have some training points. Now if I take these training points and divide it into a Voronoi tessellation, what is Voronoi tessellation? I draw these lines where the line tells me which point is the closest point. So here it will be like this, here it might be like this, here it will be like so, and then it will be like that, like that, like that, right. Okay. So this is the Voronoi tessellation, and so now basically in this we have for each training point we have its zone of influence. Okay. Within that zone of influence, that point is the closest training point. That's the nearest neighbor. Okay, so to speak. So now within each cell that we have, so this is called Voronoi diagram. Within each cell of the Voronoi diagram, I give it the value of Ti that is associated with that Xi. Okay. So here this is an Xi but also Ti pair. Okay. We have some training value, and that training value could be either regression value or it could be class value. For either of those, I just give that value for any X that is falling within that cell. Okay. So any test point that falls within that cell will get the same Ti value. So we will have these bunch of different levels in different cells, okay, and that level is flat, and that level is given to that particular cell. In one dimension it is simple to see. So let's say if we have these three training points, right, whatever training value we have here, so let's say it is regression, we will have nearest neighbor here like this, and then nearest neighbor in this zone like this, and then nearest neighbor like this. So these are the bisectors between the 2 points. So these are the bisectors. So at the bisectors we will have these level sets, and that's how we have the y versus x. Okay. So that's an example in one dimension. So that's the nearest model that we can have, that's the nearest neighbor model that we have. So here we don't have to store any parameters, we just have to compute what is the nearest training sample. So there is no parameters, it's called non-parametric model. Okay. In this non-parametric model, the downside of it is that at test time you have to compute whether a test sample is closest to training point 1, training point 2, training point 3, training point n. So you have to do n different computations, and that for a very large training data can be very cost prohibitive. The other problem is that what is the notion of nearness? Here we are looking at Euclidean distance in x1, x2 space. That may not always be the best measure of nearness. We may want to extract some features, and in that feature space we might want to operate upon Euclidean distance or cosine distance and so forth. So now coming back to the ensembles, we can actually combine several nearest neighbor models by using some in a way that is called a k nearest neighbor model. Okay. So here what we do is that we have the same x1, x2 space, and we have the same set of training points, okay. So for any test point, for any test point we will find out what are the 3 nearest neighbors, and so let us say it is a 3 nearest neighbor model, it can also be 5 nearest neighbors. So, this k is a hyperparameter. Okay. So, we can find what are the 3 nearest neighbors and we will take the average of the 3. So, if it is regression then the level is the average of the 3, if it is classification then it is the voting of the 3. We will take the average decision of the 3 nearest neighbor or the 5 nearest neighbor, and what that does is if one of the points is mislabeled, okay, or it has a noise in its target value that we recorded, then some of the other neighbors can correct for its mistakes by giving you an averaging effect. And in regression you will see that it will smoothen out some of the boundaries, or it will make the boundaries, so it will increase the number of steps that you have, because sometimes when we move in this space, the which point is the nearest neighbor, that will suddenly change because now you have more neighbors to compute and so forth. So, it will make the hypothesis class slightly richer, and it can have some sort of a smoothening effect and some sort of a self-correcting effect for label noise. Okay. So, that is another way of combining nearest neighbor into k nearest neighbor. And what is a good k? Whatever works best for your validation. Now, back to this regression models, these ensemble models. These ensemble models work not only for linear models, they also work for ensembling neural networks, for ensembling other types of networks, other type of models such as support vector regression and support vector classification. So, you can ensemble any kind of classifiers, you can even mix and match classifiers and regressors, you can take a linear regressor and ensemble it with a neural network regressor and so forth. Okay. Just remember that for regression it is model averaging, for classification it is average voting, okay, or majority voting. What we can do for classification is that if the output of the classifier is probabilities as opposed to actual classes, then we can take average of probabilities also, it becomes like a regression ensemble. But what is required is that these in ensembles that the models be somewhat independent of each other. Okay, so we will come to how we can induce that, how we can ensure that some of these are independent of each other in a little bit. Okay. Now, let us look at cascade of classifiers. So, until now what we were looking at was that we have in ensemble we have one classifier, we have another classifier, we have another classifier, and we will do a voting over that. Okay, so this is ensemble. Now, in cascade what we will do, so this is your classifier C1, classifier C2, classifier, or let us say F1. F1, F2 and F3. Okay. In decision tree or in cascade classification, what we will do is we will first use classifier F1, okay, and let it divide the data into, let us say, 2 classes or 2 different bifurcations, and we assume that this bifurcation is not perfect, at least for the test data. So, we will refine that using another classifier that will actually give you a better decision. It specializes on what comes to the left branch as opposed to what goes to the right branch using F1. Okay. So, now what you will get here is different outputs. So, you will get the F2 output, but you will get it only on those samples that are sent to the left branch by the first classifier. Okay. So, this is a cascade, like a cascade of waterfalls, one falls into the other. Okay. So, here we have the final decision, decision 1, 2, 3 and 4. Okay. So, each of these classifiers in the cascade might be a weak classifier, okay, but when we combine them in a cascade, then they may give us better decisions. So for example, what we are saying is that let's look at linear classifiers. Okay, so we have one linear classifier which is F1. Okay, so now here it's possible that so let's say these are your positive points. These are largely positive. Okay, some of them are negative. These are largely negative. Okay, some of them are positive. Okay, so this is the best we could do with a single linear classifier. All right. Now, whatever goes on the upper side of this classifier, we will learn a second classifier which is F2. Okay, and we will learn a third classifier which is F3. Okay, so by doing a cascade of the three, notice that they are not intersecting each other in ensemble. So this is cascade. Okay, in ensemble the same effect look like this. Here the three classifiers were, their boundaries were overlapping with each other, and then it was dividing the space into more than two subspaces. Okay, here what we have is that they are not cutting each other. Only if something falls on the top side of the yellow line of the F1 classifier, then we will apply the F2 classifier. If it falls on the lower side of F1, then we will apply the F3 classifier. Okay, so based on that we may get better decisions in a cascade. So now let's so it's basically called a tree in the sense that these are called, let me change the color, these are called leaf nodes. What is a leaf node? At the end of the leaf node you will get a decision. Okay, and this the nodes that are not the leaf nodes, they are called internal nodes. So they don't make the final decision, but they help you reach the final decision. And this could have multiple branches, and it need not be just three classifiers with two levels. It can actually have many such decisions, and it need not even be balanced. Okay. So in that case, the special internal node where we start, okay, that is called the root node. So it's an inverted tree. The root is on the top and the leaves are at the bottom. In actual trees that you see outside your buildings, the roots are at the bottom and the leaves are on the top. Okay. So here the first node where the data enters, that is a root node, and all the other nodes below that are either internal nodes or or leaves, and the leaf nodes are where the final decision gets made. Okay. So this is a cascade, and usually they can be implemented as binary classifiers, but there is no strict requirement that they have to be binary. Let's say if it is a cascade of neural networks, the neural networks can also be n-ary classifiers if we have more than two classes. So these binary classifiers can also in a cascade work for multiple classes also, because it's possible that at every node you only make a binary decision of, let's say, class 1 versus all the other classes, class 3 versus all the other classes, and so forth, but finally you make a decision for one class. So all these potential combinations are possible, and they are all called decision trees. We'll look at a simple version of a decision tree. Let's look at a special type of a cascade classifier called a binary decision tree, and the structure of the tree is quite simple. At each node we will make a binary decision about whether a particular feature is greater than or less than a particular threshold. That's all we will do. Okay. So what we mean by that is that, let's say we have a tree structure, and this tree structure goes like this. Okay, something along these lines, and all we do is at any given node, what we will take is we will take one dimension of x, not one sample but one dimension of x, so xi, okay, and we will see whether it is greater than some threshold theta j, okay, xi greater than theta j, okay. So if it is greater, then we will go here, which is yes. If it is not greater, we will go here, which is no. That's the decision we will make. Okay. So it's a binary decision at every node of the tree, okay, whether it is a root node or any other internal node or a leaf node. Just that when we have the leaf node, what we will do is, sorry, any internal node, on the leaf node what we will do is we will give the decision. So for classification it would be one of the class labels, okay. For regression it would be one value, it will be one continuous value, so it will be some value which is y, yi, yj, etc. So we will get these step type outputs for regression, and we will get some class for the classification. Now what does the hypothesis space looks like? So basically what we will have is, let's say if we have only two variables, which is all I can draw. So if I have x1 and x2, okay, your root node is going to select either x1 or x2, and if it has selected x2, then it will basically draw a line which is parallel to the x1 axis, alright, which will divide the points into x1 greater, so we will have this x2 greater than theta 1, that is the decision we are making. So this is the yes part and this is the no part. So this is, let's say, x2 greater than theta 1. Okay, so this is the yes part and this is the no part. So all points, training points, will be divided into one of these two sets. Either they are yes as per the root node or they are no as per the root node. Once they are divided, they will go to, all the yes ones will go here to this node, all the no ones will go to this node. Okay. So now let's change the colors a bit. So for all the yes ones, we will have another decision, and that decision, let's say, could be based on x1, okay, x1 greater than theta 2. Okay. So here we have x1 greater than theta 2 is x1 greater than theta 2, and then basically this is your yes and this is your no. So this is your yes and this is your no. Okay. Similarly on this side, the next division for this node need not be x1 now, it could even be x2. So we could have, for example, let's take a blue color. So let's say this particular node, it could even be x2. So we have another x2 greater than theta 3. Theta 3 is some parameter, some threshold. So now we have yes here and no here, for example, right. So we could have many of these divisions, and then we can color these divisions based on the color of the class. Okay. So we can get many of these axis aligned divisions, and they will all be in a cascade, they will be nested in, they will be half spaces of half spaces and so forth. Okay. So that is the hypothesis class that this decision tree is implementing, and this is how it is dividing the input and output space. Okay. Now the question is, what is a good way to choose which variable and what threshold we should have at every node? That is basically what the algorithm, the learning algorithm, has to figure out. But what it is actually implementing, whether the implementation is good or not, is what you see on the right hand side. You will get all these boundaries which are axis aligned, they are not slanting, and when they are axis aligned, they will split the space into two half spaces, top, bottom, or left, right, or in 3 dimensions it will be more complicated and so forth. And those will be yes and no, and then within the yes and no there will be multiple yes and no's when you go down into the tree. Okay, so that's the hypothesis class of a decision tree. Now let's see how we are going to split each node. So we are going to use a greedy algorithm. What I mean by greedy is that when we are doing one step of the learning, it tries to maximize something, whereas when you take all the steps of the learning together, that local maximization for one step may not have been the optimal way of doing so. But we are greedy at every step, we are trying to maximize something at each step. So what is it that we are going to maximize? We are going to maximize the purity of branches. So what is purity? So let's say you have the root node. Okay, in this root node we get all the training points one by one. Okay, so we have now the index that I'm using 1 and 2, it's not the dimension, it is the index of the training point. So I get x1 t1, I get x2 t2, right? I get x3 t3, etc. up to xn tn. Okay, all these training points I get. Now these training points, these, what are these t1, t2, tn? These are, let's say, two classes, either class 1 or class 2. Okay, so some of them are class 1 and some of them are class 2. All right, so these class 1 and class 2 makes all the nodes all the training points coming to this first node to be impure. It's not purely class 1, it is not purely class 2. Okay, what we would like is that we should find a decision in such a way that what we get on the 2 is purely class 1 and purely class 2, or vice versa, but not a mix of the two. It's either purely class 2, purely class 1, or purely class 1, purely class 2, but not a mix of the two. We want purity. So what is that definition of purity? So this is less pure, all the points coming here are less pure, but when they are split, okay, some points, some n1 points will go to left side and n minus n1 points, which is n2 points, will go on to the other side. Okay, so these are n points and these are n1 points, these are n2 points. We would like n1 and n2 points that are split to be pure, even though n points may not be pure. So let's not say purely C1, purely C2, let's just call them more pure, because we may not have the perfect decision. Okay, so more pure means predominance of one class over all the other ones. Okay, so what is the notion of this purity? How can we capture it mathematically? Okay, so one way to capture it, there are multiple ways of capturing it. We can say that we can say max over C of all the PC. What is PC? PC is probability of class C. Probability of class C, and let's say there are C classes that belong to 1 to capital C. Okay. So all these PCs will add up to 1. So sigma over C PC is equal to 1. Okay, and PC is greater than equal to 0. Okay, it's greater than equal to 1. Right, so that's a probability mass function. We want max PC to be very high, so that means it is very pure. Okay, so what is PC? PC is the probability of all the classes that are coming to, now let's define this a bit, that are coming to the ith node. Okay, so this is node 1, this is 1, this could be 2, this could be 3. Okay, so all the training points that are reaching that particular node or that particular branch, we are looking at the probability of those, and we don't know the probability, but what we are going to do is we are going to model that probability. We are going to model that probability as number of points in class C divided by all the points that are coming to that node. It's an empirical estimation of that probability. So that could be one way of looking at purity. Okay. The other way of looking at purity is to look at entropy. Okay. So entropy doesn't look at just the max, it will look at, so your entropy is going to be negative log of negative estimated value of log of Pc. So Pc times log of Pc summed over C. Okay. So this is the entropy. Okay, so that's another measure of purity, or it's rather a measure of impurity. High entropy means high impurity. So negative of entropy, where this negative sign is dropped, is going to be purity. Okay. So this is impurity. Another way of looking at it is that if you have similar to this Pc, we can have sum over C, Pc 1 minus Pc. Okay, so imagine if one of the PCs is very high, right? Then so this is another measure of impurity. This is called Gini impurity. Okay. So here, if one of the PCs is close to uniform, that means it is close to 1 over the number of classes, 1 over C, then or all of them are rather close to 1 over C, then what we will get is the lowest Gini index. That means everything is equitable, all classes are equally represented, and that is basically high impurity. And otherwise what we will get is low impurity because of this 1 minus Pc part. Okay. So it is maximized when all the PCs have the same value, which is 1 over C. Okay. So these are three different ways of measuring. So this is measuring impurity, and this one is measuring purity. So we can take negative of any of these to convert it to the other. So as we were saying that we split a node in a tree based on what kind of a split will give us maximum increase in purity or the maximum decrease in impurity, and that is based on the training samples that are coming to a particular node, right? So they may be impure, which means they are mixture between two different classes, whereas when they are split into two different branches based on a single decision of yes or no, then the two branches have predominantly training samples from only one particular class. So that is basically increasing the purity of the split. So now this purity itself may not be balanced, in the sense that we may send only one sample to one branch and all the other n minus 1 samples to the other branch, which does not help, right? Because we want to have a better average purity. So we want more balanced purity increase as opposed to imbalanced purity increase. So let us see what that means. So let's say we have a particular branch in which we have a lot of training samples reach that branch, right? So let's say there are one particular node. So let's say there are n0 samples that reach here, and then we want to split them into two different sets of samples. So here there is the decision, right? And this decision is either yes or no, and based on that we get n1 samples that go here, n2 samples that go here, such that n0 is equal to n1 plus n2. Right. Now further, let's divide that into multiple classes. So let's say we have n0 samples of class 0 and n01 samples of class 1, and if we add them up we will get n0 samples. Similarly, we have n10 plus n11 samples that will give us n1 samples. We have n20 plus n21 samples that will give us n2 samples, and on top of that n1 plus n2 is equal to n0. Okay. So this is how the split is working. So the second is an indicator of class, and this is an indicator of branch. right. So if n1 is equal to 1, right, if n1 is equal to 1, then that's a pathological case in the sense that we will get only one sample and it will be by definition pure because it will have only one class. So we want some balance metric. So the way we will define the purity is that, let's say we have entropy, right. So that entropy will be balanced, or it will take the weighted entropy, where the weight will be based on the number of samples it is representing. So so first we have to define the classes, the probabilities themselves. So what is the probability of class 0 when it is coming on the n0 branch? So that probability is going to be n00 divided by n0. Okay. So this is probability of class 0 at the 0th branch. Okay. And similarly probability of class 1 is going to be n01 divided by n0. So what is the entropy here? The entropy is going to be n00 n0, okay, log of the same thing, n00 by n0, okay, plus n01 divided by n0 times the log of the same thing, log of n01 divided by n0, okay, and we will take the whole thing and we will take the negative of that. So that is the entropy of the decision of the samples that are coming into n0. Similarly, we can define the entropy of the samples that are going to n1 and the entropy of the samples that are going to n2. Let's just call this E0. So we have E0, we have E1 and we have E2. So what we want to do is we want to compare the average entropy. Okay. So the average entropy is going to be n1, okay, which is the number of samples that are going towards the first branch, divided by n0 and E1, and then we will add to that n2 divided by n0 times E2. So this is the average impurity or the average entropy of the split, and this is something that we want to minimize. We want to minimize this entropy, we want to maximize the purity. Okay. So these weights, now you can see that if n1 is just a single sample, then obviously the entropy is going to be low, but what we will also see is that the weight of that is going to be low. So then the average, the weighted average will be dominated by the other branch if it has more samples, where n2 is, let's say, much larger than n1. So this gives us a sense of balance of how to do the node splitting. So now the decision that we have to make at each node is, for each variable and each available threshold, which variable and threshold combination gives us the maximum decrease in impurity or the minimum entropy, minimum weighted entropy. Okay. So now the complete algorithm for the node would be that for all variables, okay, for all thresholds, okay, for all training points that reach this node, okay, what do? We compute the correctness of decision, okay, and then once we have done that, then for all thresholds what we will do is we will compute entropy of two branches, okay, then compute weighted entropy of the split. Okay. And once we have done that for all of them, then pick split with minimum entropy, minimum weighted entropy. Okay, so that is our complete algorithm for a particular node, and we will keep repeating it until one condition that I have, termination condition that I have not written, check if the weighted entropy is minimum, which means that everything is pure. If everything is pure, then we will not split, otherwise we will recursively split. Recursively split children, the two children nodes. And there is a termination conditions, we do not recursively split if we have already reached a desired level of purity. Okay, so that is our complete tree algorithm. Basically start at the root, okay, split node, and within split node what we have is recursively split node, the children nodes. Okay. So that is pretty much the entire tree learning algorithm. And what can happen with this is that sometimes we can do overfitting. So let's say we have the root node where all the training points come, and after that we split them into two branches, and in a pathological case we can keep either in a well balanced case all of them will split into two branches. In a pathological case only one of them will split into two branches, and we can keep doing that. And let's say the final ones, these are all, let's say, leaf nodes. So I will draw them differently. Where your depth is now going to be n minus 1, but there could be other reasons why you could have very large trees even if the depth is proportional to log n. So what will happen is that ultimately if we keep doing this, these are all going to be pure nodes, because these will have, all the leaf nodes will have only a single element in a worst case. Okay, they will have a single training element in the worst case. Now the problem with having just a single element is that this will tend to overfit, which means that in the x1 x2 space, right, we will have lots of axis aligned decisions, and we will create lots of like small region boundaries, small regions where there will be only one training sample, and we can color it whichever way we want. What we actually want is that we want a particular leaf node where there are more than one training sample, so that this tessellation is not very fine, it is actually coarse, so that we think that will generalize better. So because of that, what we can do is, once we have trained the network, we can prune it. We can say that I will only use up to this depth, which means that whatever came after this depth will actually not be split further, but it will be given its own leaf node. And it is possible that because of that some of the training samples will be misclassified, but so be it, which is the regular trade-off that we have in bias versus variance, that we tolerate some error in the training data set for better generalization to improve overfitting, so to reduce overfitting. So the general algorithm for training for preventing overfitting could be that keep a validation data set separate, and after each split test whether the accuracy on the validation data set has improved. If so, then we do not split any further, then it is not really pruning, it is basically controlled growing of the tree. But the other could be that we completely grow the tree and then we arbitrarily cut it at a particular level, and anything that goes below that we will treat it as a leaf node. So with the learning of a tree, we can generalize even better by taking an ensemble of trees, which is called a random forest. So what we can do is we can take one particular tree, and then we can take another tree, and then we can take a third tree, and we can take the average of their decisions. So now if we want three different trees and if we can take the average of their decisions, there has to be something different about these trees, otherwise they will all give you the same decision. So that difference between trees, if you use a greedy algorithm, the way I showed before, then we will not get different trees. We will always get the same tree no matter how we start the training. So to randomize the trees, right, so that they are different from each other, there is a trick that is used. That randomization is basically that at each node we don't try all the variables for splitting. So let's say we have 100 variables, we will randomly choose 5 variables, okay, randomly select 5. Okay, this is more general. So let's say we have 1000 variables, we can randomly select 10 variables or 7 variables or something. So randomly select a subset of variables and make the decision to split only among those 5 variables, not over all the variables. So that brings the randomness, because of which all the trees will grow differently, and because of which we will have an ensemble effect that we can use. So this brings us to the new topic, that how can we randomize models so that we can ensemble them better. So obviously one of them in random forest is to randomize the variables on which we will split each node, and it happens at each node. So variable subset selection, that is randomized, which is the case in random forest. For neural networks, we can randomize the initialization, and it works only for non-convex models because then you converge to different local minima, and we can select different subsets of the data, which also leads to different models. Let's look at it more carefully, all of these. Okay. So random initialization could be, let's say you have a neural network, right, and this neural network has these weights and biases. So these are your hidden neurons, and then we have some input neurons that supply input to these neurons, right. So these weights and biases can be randomly initialized. Between different neural networks, the architecture may be the same, and because of that we will get another neural network, okay, and a third neural network, and so forth, and all these neural networks can actually give you different results, and then we can ensemble their results. We can select a different subset of variables, alright. So we can also do that for neural networks, for example, or SVMs, for example. So let's say if you have 100 variables, okay, then randomly select, let's say, 20 variables and train an SVM on it, and then randomly select another 20 variables, train SVM. Okay, and do that multiple times, and then take the average of these models, and that will give us an ensemble. We already saw how this is done for random forests, where at each node we select a subset, not at the model level but at the node level, and that gives us different trees within the random forest. We can also try random subsets of data. So let's say this is your training data, and they are differently labeled. So we can have one subset that selects these samples, we can have another subset that selects a different set of models, different set of training samples, and so forth. So we will have one model trained on this, another model trained on this subset, and these models will turn out to be different, and then we can average their results for validation and testing. So this randomization basically breaks the dependence between models, and once that dependence is broken, we can see that if the models are truly independent, then ensembling them will give us better results, which we have seen before. There is a particular way of combining models where we don't train each model separately, but we train them sequentially, and that is called boosting. So the reason behind sequential training is that once we train them sequentially, basically for each model we are aware of the shortcomings of the previous model, and we train the current model based on those shortcomings as opposed to independently by randomizing either the input variables or the initial stage or the variables that we are selecting. So here how it will work is that, let's say we have a data. Okay, here let's say the data itself is equally weighted, all samples have the same weight, and that data gives us model 1. Okay. And this model is a weak learner in the sense that it does not do a perfect job. It can learn better than chance, but it cannot do a perfect job of learning on the training data. So now what we will do is that we will take the data forward for the second model. But in addition to taking the data forward, we will also give some weights. Okay. So we will give some weights, let's say D1 weights or D2 weights, let's call it D2. So D1 weights were uniform weights. So D1 weight means that all the data points are taken as the same weight. Plus we will take the error of the model 1. Okay. Based on that we will train model 2. Okay. Then we will propagate the weights for the third iteration and so forth, and it can go for multiple iterations. And we will also give the error of model 2, and based on that we will get model 3. And our combined decision is going to be a weighted average of the 3. So weighted, and again this will be weight I and then prediction I. Okay. So what is the weight here? The weight is that the model that does a better job of predicting will get a higher weight, the model that does a poorer job of predicting on the training data set will get a lower weight, obviously. And then here we require these models to be such that they can work with, work with different importance given to different training samples. So for example, in logistic regression we have the logistic loss, but inside the sum over all samples we can easily add a weight and not assume that all of the samples have the same weight. Same with neural networks. This is something that we may not be able to do for certain other models, but for several of these models, including even SVM, inside the hinge loss we can have non-uniform weight for different samples. So a lot of these can work with boosting. So there is a particular form of boosting that is called adaptive boosting or AdaBoost that we will look at in more detail. That basically tells us how to compute these weights and how to, so there are other weights here, there is W1, W2 and W3, and how to compute the weights of the models themselves and the weights of the data points in each iteration. So now let us look at adaptive boosting. So essentially the summary of the model is the following. Initially set uniform weights for all samples have the same weight. So let us say 1 by n, if there are n samples all of them have 1 by n weight. Okay. Then in each round we are going to train one model, and finally we are going to combine these models. So in each round when we are training the model, we will create a bootstrap sample based on the weight. So bootstrap sample means we will take a subset of the data samples and we will compute the weights for these samples. Okay. We will create a classifier, we will train a classifier that will that will be based on this sample, and we will apply it to the original training data set. Okay. Then samples that are wrongly classified, we will have their weights increased. Samples that are correctly classified, they will have their weights decreased. Alright, so we will need an algorithm for that. So in the next round, the next model will try to classify the wrongly classified samples more than it will try to correctly classify the previously correctly classified samples. Obviously, because now we want a model that can compensate for the flaws of the previous model. Okay. If the error rate is higher than 50% or chance, then we will start over again. We will actually not even take this model into consideration. So the model has to be better than chance, which means it has to be a learner, it has to be at least a weak learner, and then we can actually put it in the kitty of models, in the group of models, and then we can combine it. So final prediction is the weighted average of all the weak learners that we have trained in the previous rounds. Okay. And that will give us the final training accuracy. So now let's look at the details. So the details of the model are the following. So let's assume that our training data set is S. Okay, that is our training data set. And we will initialize that the weight of each sample D1 is going to be 1 by n. That means each sample gets the same weight. This is a uniform weight for all the samples. Then we will have m rounds of different model training, and within each round we will get different models. So here we are going to learn a weak learner WL, okay, on the training data set S, but with weights dm. So which is for D1 it is all uniform weights, but now these weights will change as we go down to D2 and D3 and D4. The weights will change such that the weight will be increased for those that were misclassified by dm minus 1. Okay. So we will compute this epsilon m, okay, which is the error rate of this particular model, and that is, or the weighted error rate. We will just take the weight of each sample and we will multiply it with whether we correctly classified Ti yi as Ti or not. So what that means is, this particular notation, as you know, means this stylized one means it's an indicator variable. This variable is either 0 or 1. This variable is 0 when the condition is not satisfied, and it is 1 when the condition is satisfied. What is the condition? That there has to be a misclassification, inequality sign. So when your prediction yi is not the same as the training label Ti, okay, then we are going to have this variable as 1, otherwise we will have the variable as 0. So obviously when epsilon is large, that means there is more misclassification, and it is also based on the weight of the sample. So it is not just the misclassification, it is weighted misclassification, where the weight is dim. Right. And then we are going to compute the weight of the entire model, and that is based on a log transform. So this log transform, basically we will take the inverse of this the epsilon, which means that we will have high weight for those models that have low error. We are not going to have a high weight for those models that have high error. Okay. So now this gives us the model weight. This is your model weight, and we now also need to recompute sample weights for the next round. So what are your sample weights? Sample weights are such that the misclassified samples will have more weight and the correctly classified samples will have low weight. So assuming your Ti is Ti belongs to +1 and -1, right? So your Ti belongs to -1 and +1, okay, and Yi also belongs to -1 and +1. Okay. We are going to have, we set up the weights such that we take the weighted almost like a soft max, right? So basically if these two are the same if we look at Ti and Yi and both have the same sign, then this product is going to be positive. When the product is positive with a negative sign, it becomes a negative, right? So basically we get a lower number here, okay, and we will weight by the overall accuracy, weight based on the overall accuracy of the model, and then we in the denominator we have all the other samples. So based on that we get now a new weight which is not uniform, it is non-uniform, it all adds up to 1 again because of the denominator, the way it is set up. But now we have a reweighing of the samples and we can iterate and go into training the next model. So essentially what this is doing, and it can be proven, although we will not go into it here, that AdaBoost is trying to decrease the exponential of the error in each stage. And your final prediction is going to be, we take all the predictions weighed by the model's weight and we take the average based on that. So that is the how we will combine all the models. And essentially, let's say if our weak learner is as simple as a threshold, axis aligned threshold, what we are doing is we are taking multiple of these weak learners and we are combining them, and based on that we are getting a larger hypothesis space that may give us better classification on the training data, even when the underlying models are quite simple. So this AdaBoost has been quite successfully used in detecting faces before deep learning came into wide use, in something called Viola-Jones face detector using Haar filters. So Haar filters are basically, we detect features from images using very fast filters. Basically what we do is we take these positive and negative bars and we just see whether we convolve these with the images to find whether we have horizontal bars or vertical bars and so forth, but vertical lines and so forth. So once we have extracted a lot of these fast wavelet like features from the images, we have a lot of these features. On top of that we train a AdaBoost model and that becomes a Viola-Jones face detector, which is standard package in OpenCV that you can use for detecting faces, and does pretty well and it works very fast. So this brings us to the end of our discussion on combining models. I hope you can now take simpler models and find different ways of combining them to make them into more complex models that will give you better performance than an individual model. Thank you.